and thank you all for coming. So I am going to give first a quick update of the passive source seismic in GSWA, and then I'll come back with some preliminary passive source seismic models for the Southwest Yilgarn. So the passive source seismic or earthquake seismology has been used widely for mapping the Earth interior from the core to the crust. Here in the survey, we are particularly interested in the whole lithosphere architecture. We target structures like various velocity domains, domain boundaries, and velocity discontinuities. For example, the Moho and the base of the lithosphere. These are very important structures which contain critical information regarding regional tectonics and mineral systems. GSWA's involvement in this field has been so many years. The red dots here are various seismic stations GSWA helped and or installed through the past years. These are through various projects, collaborative projects with universities and research institutes. And in late 2022, it's not flipping. Okay, we decided, how about let's do our own. So with the funding from the state government, we initiated this massive 10-year WA Array project in November 2022. The plan is to cover the whole state with 1,600 passive source seismic stations with 40-kilometer station spacing. This makes WA Array one of the densest regional seismic arrays in the world. So far, we have successfully covered phase 1. So that's the small area here, close to Perth. And then by this time, we've finished about 80% of the phase 2 installations. And then the rest, about 40 stations will be installed in the coming 3 weeks. So by the end of this year, we'll start pushing out products like the whole across-scale lithospheric models. For example, the cover thickness map, the Moho topography map, the thickness of the lithosphere, and various 3D velocity models. We are also collaborating with other research institutes to develop models of other lithospheric models. So here, I guess, for this forum, we actually have very good coverage for the Southwest Yilgarn. The map here shows the black triangles. That's our phase 1 WA Array stations. The open triangles are the previous seismic deployments. And the red one is from the SWAN project, which is the ARC linkage project led by ANU, and we're part of the collaborators. So I'll quickly show the two most commonly used passive source techniques, receiver functions and ambient noise tomography, and then I'll come back with the models of these two. So receiver functions, by the name, receiver means seismic stations, functions means the structure underneath. So it actually uses the body waves from faraway earthquakes. Like in this case, in this example, the incoming P wave reaches the bottom of the Moho beneath the seismic station. Part of the P wave energy is transmits across the Moho and reach the station. That's what we call the direct P wave. And part of the P wave energy here is converted to the S wave, which travels slower. And then that's what we see here as the PS or P Moho as signal. And these both transmitted and converted energies sometimes can be trapped in the crust, and then they just bounce up and down, and then they reach the station. And then we call these the multiples. These are these guys. And receiver functions are really sensitive to the velocity gradient, for example, the Moho here. So this is really good to see how deep the Moho or other crustal structure, how deep they are. The other technique is, okay, here's the real example from WA Array, one event, and you can see the Moho face very nicely. And down here, these are the multiples. And the other technique is so-called ambient noise tomography. By the name, I guess you can probably tell this one doesn't need earthquakes at all. So the trick here is we need station pairs. Like in this case, we have two phase 1 WA Array stations, WZ08 and 018. These two record waveforms at the same time. These are two 12-minute waveform cuts. By the look at it, you don't see any earthquakes, and this actually records what we call ambient seismic wave field, which contains the energy from ocean waves, sometimes small local earthquakes, and of course mining blasts in WA. So the trick to do this so-called ANT is first, let's do a cross-correlation of these two. That's the cross-correlation waveform of these two. Probably you cannot see much. I can't see anything either. But the thing is, you can stack. I only had 12 minutes for the first one. And then you can start by stacking an hour-long data. And then this is a day, all the way to 3 months. You can probably see some coherent signal starts to emerge roughly after a day. So this is we call interstation surface waves. Basically, it means this is sort of like the surface wave propagating between these two stations. And we have all these stations. We can form all the possible station pairs. And in the end, this naturally gives us a tomography inversion problem. And this is really good to retrieve 3D velocity, in this case, shear wave velocity models. So coming back to Southwest Yilgarn, I will present two models, the receiver function model and the ambient noise tomography model, courtesy of the ANU group. So 3 lines, first along the southwest seismic line, and 2 other lines which cut diagonally across phase 1 coverage. So this is the active source line, west is left. The top is the depth migrated receiver functions. It's sensitive to velocity gradient. So in this case, you can probably trace the Moho all the way from here, and then across Darlington, you don't see much. And then here you see maybe a East DP Moho or some sort of imbricated Moho, and then very weak Moho signal here, and then a strong Moho, another weak Moho. So I still have like several terabytes data to put in here, so this is not final. But I guess if you compare this with the big map over there, you can actually see a lot of consistencies. And I probably needed to point out, Ralph mentioned this mineralization surface. So I remember I saw something here, and something here, another one here. So these are all like where you don't see a clear Moho, or you have Moho truncations. The bottom is the is the ambient noise tomography. Basically, it shows the absolute shear wave velocity information across this along the same line. First of all, you see the big Perth Basin signal, and across the Darling Fold, you see some sort of high velocity mid to lower crust. In general, the whole southwest terrain has relatively faster mid to lower crust. And across this boundary, you have this, I guess, Yuan shear zone. You have some sort of slow mid crustal velocity. So this is for the active source line. This is the line from southwest here all the way to northeast. Well, you see totally different Moho image. Again, I guess the Darling Fold is really something. You don't see the Moho, but the rest of this part of, or the central to northern part of the southwest Yilgarn probably has sort of uniform Moho signature. But you do see some sort of weakening along these big structure zones, which means these are probably whole crustal features. And the bottom one, again, is the shear wave velocity model, the Perth Basin here. And then this whole region is sort of fast mid to lower crust. And then last one is this one. I just cut it this way, but it happens to go sort of following the new, what's the name again? The new terrain here, the blue one. I guess I need to point it out. Okay, you see this large Moho signature, which is pretty much the same one as the previous line. And this is just the north. And if you look at this one, 400 kilometer distance, that's roughly here. So the whole part from roughly 100 to 400, this is similar to the previous one. And it has very strong Moho. And then at 400 kilometer distance, you see this double Moho feature. And on the right-hand side, or south of the line, it's totally different signature. I guess this suggests at least you, from the Moho or the receiver function image, you can see some sort of a north-south distinction in this part of the Yilgarn. I think I've already there, so that's all I have. I have the images printed there, so if you want to discuss more, let's do it later. Thank you very much.